Hello learners, I am Dr. Shongita Das, Associate Professor of Department of Basic Science and Humanities, Institute of Engineering and Management, IM Kolkata. So the topic of this video lecture is oscillation. So before jumping to the equation, let's start this video with an important question, that is, why do we need to study this topic? We know that oscillations are present everywhere, starting from the nature to the complex engineering structure. Start from simple pendulum to the vibration of the guitar, from electrical circuits to the atomic vibration. It is present everywhere. Now, studying oscillation will help you to understand how a physical system behave under certain conditions. It also helps us to understand the mechanical stability of the system and how this system will evolve with time. Even if it is a bridge, even if a circuit of a electrical circuit, how it will change with time, that we will understand in this lecture series. So, the important goal of this video lecture is to understand mechanical stability of the system, to study the time evolution of a physical system. Now, the learning objective of this particular lecture. Here we will learn about the oscillatory motion. Also, we will try to understand the basic characteristics of simple harmonic motion through the everyday example. In every day, we encounter different kind of motion. Periodic motion is one of them. Now, any motion that repeats itself after a definite interval of time is called periodic example. There are numerous examples. Here I have given only two examples. One, the moon is revolving around the earth and it takes certain interval of time. Here, one clock pendulum is ticking and the pendulum is executing to and fro motion with a certain interval of time. So, this is describing periodic motion. Now, among this periodic motion, some are oscillatory motion, and we will specify this oscillatory motion to those periodic motion where an object moves back and forth, that is a to and fro motion about a central position. Let's describe this example. Here I already have told you that it is a pendulum. Okay, clock pendulum, and the mass of the pendulum bob is executing to and fro motion around a certain central position, and also the hands of the clock also executing periodic motion, and it will move to a complete circular motion after a certain interval of time. And there is another example that one frog is swing in the swing and it is executing to and fro motion. Here, the motion of this frog is actually a oscillatory motion. The motion of this pendulum bob is an oscillatory motion, but the motion of the hands of the clock are not oscillatory motion. It is periodic, but it is not oscillatory because it is not executing to and fro motion about a central position. So, from this example, we can say that all oscillatory motions are periodic, but not all periodic motions are oscillatory. So, move to the next slide. Here we have a simple pendulum, and when a pendulum and it is executing to and fro motion, and we can here describe one term, that is force of restitution or the restoring force, and this restoring force comes into play or into play when there is an oscillatory motion, and it tries to displace the particle back to its position of equilibrium. And this is in general a function of displacement. So I can say this, let me throw the pen. So here there is if the force of restitution is actually function of r, and here r is the displacement. Okay. And we will define the simple harmonic motion, that is a special type of oscillatory motion. And for simple harmonic motion, the vibration under the action of restoring force is directly proportional to the displacement. So here, this mass, we have a mass spring system, and it is executing to and fro motion. And this red line is actually the equilibrium position. When it is away from the equilibrium position, a restoring force is acting on the body so that it comes to the again to the equilibrium position. And for this, F is proportional to x, where x is the displacement. So if I define x as my displacement, this restoring force or the force will be proportional to x, and there will be a minus sign because this restoring force will act in the opposite direction of my displacement. Or I can write is equal to minus kx, where k is the constant, proportionality constant. So here a particle undergoing SHM is called the linear harmonic oscillator, and the vibration or the oscillation in a mechanical system results from two basic properties. One is the inertia and second is the elasticity. And since here you can see this F is actually proportional to x to the power 1. It is a linear equation. That's why it is called as the linear harmonic oscillator. Okay. So this is the special kind of oscillatory motion where the restoring force is directly proportional to the displacement. Okay. Next, the various characteristics of the SH. The motion is periodic as well as the oscillatory, that we already have discussed. Second, the restoring force acting on the particle. Here, this is the particle that is executing the simple harmonic motion, is directly proportional to the displacement of the particle and is directed opposite to the displacement measured from the mean position. I already have described that F is proportional to x, and there is a minus sign because it is directed opposite to the displacement. And we know F is equal to mass into acceleration. So the acceleration of the oscillating particle is always directed towards the mean position of its path. And the motion of the simple harmonic oscillator always takes place in a straight line. So these four are the characteristics of the SH that you need to remember. Next, here we need to find out what will be the equation of motion. That means how the physical system is evolving with time. Now all of you know the Newton's law, that F is equal to mass into acceleration. This is mass and this is acceleration. And if I define y as my displacement, then dy dt will be the velocity and d2y dt2 will be my acceleration. So here m d2y here in this equation, m d2y dt2, this term is actually the restoring force. M into d2y dt2 is equal to minus k into y, where y is my displacement, okay, and k is the proportionality constant, and also this k is known as the stiffness constant of this mass spring system, okay, and also this is the restoring force per unit displacement. So I can write, or we can simplify this particular, this particular equation as m d2y dt2 is equal to k minus ky. Now dividing in the both side, I can have d2y dt2 is equal to minus omega square. Here omega square is defined as k by m. Okay. So minus omega square by y. So this one, so here this equation is the, this is the equation of motion. From if I find so this is a differential equation. If I found the general solution, I can have the how the equation I can have how the equation, or how the physical system is evolving with the time. So this is the equation of motion, or EOM, of this particular physical system. And this is a second order linear differential equation. Now, pause your video, and here there is a small home task for you. So write down this question. The resultant force acting on a particle executing simple harmonic motion is 20 Newton when it is 8 centimeter away from the center of oscillation. Find the spring or the force constant. So you need to find out the what will be the value of K. You know the F is given here. You know the Y that is given here. So you need to find out the K value. So student, do it fast. I am moving to the next slide. So I already have discussed about a spring mass system. So before going to the exact solution of that simple harmonic oscillator, just quickly let me give some of the review some of the mathematical tricks. So a system with 1 degree of freedom is linear if its equation of motion is a linear function of coordinate y that specifies the system's configuration. And also the equation of motion must be a sum of terms, each of which contains at most 1 power of. And this is the general form. This one is the general form for this differential equation that will describe this equation of motion. Alpha d2y dt2 plus beta dy dt plus gamma y is equal to f of t. And I think you know this is not an homogeneous equation. This is an inhomogeneous second order differential equation. So what will be the homogeneous form? So if I take this f of t part to be 0, then it will be a homogeneous. And of a homogeneous equation, what will be the general solution? So if y1 of t and y2 of t are the two solutions of this equation, then alpha d2y dt2 plus beta dy dt plus gamma y is equal to 0. 0 of this equation, y1 and y2 are the two solutions. Then also it is said that their linear combination is also a solution of this particular equation. That means that the general solution of y of t will be given by a y1 of t plus b y2 of t, where a and b are the arbitrary constant. So this is also a solution. So y1 of t is one solution, y2 of t is one solution, and linear combination of y1 and y2 is also a solution of this particular linear homogeneous differential equation. And we need to apply this thing in the later sections. So please remember this thing. Let's move to the simple harmonic oscillator. So what we have, the general equation as alpha d2y dt2 plus beta dy dt plus gamma t is equal to 0. And if I put that alpha equal to 1, beta equal to 0 and gamma equal to omega square, then we will have this familiar simple harmonic oscillator equation of motion, that is d2y dt2 plus omega square t is equal to 0. And our aim is to find out a general solution of y that will describe the time evolution of the system. So here, for this, we will assume one trial solution. Say our trial solution is e to the power mx. I think all of you know how to do differentiation. So we will find, this is a function of time. So y e to the power alpha t. So we will find out dy dt is equal to alpha e to the power alpha t, and d2y dt2 will be alpha square e to the power alpha t. Okay. So let me just rewrite it here again. d2y dt2 plus omega square y is equal to 0. We have y is equal to e to the power alpha t, and I just forget to mention that here alpha is a non-zero constant constant. So if I put d2y dt2, that is alpha square e to the power alpha t plus omega square e to the power alpha t is equal to 0, or I can write alpha square plus omega square e to the power alpha t is equal to 0. Now this exponential function cannot be 0, so the only option is alpha square is equal to minus omega square, or I have alpha equal to plus minus I omega. So here we have two roots. Alpha 1 is equal to e to the power alpha 1 equal to I omega, and alpha 2 is equal to minus I omega. Okay. So the general solution can be written as, so alpha 1 equal to I omega, this is one solution, and alpha 2 is equal to minus I omega, this is another value of alpha. Okay. So the most general solution will be written as A e to the power I omega t plus B e to the power minus I omega t, where A and B are the arbitrary constants. Now, from Euler's theorem, we know that e to the power I omega t can be written as cos omega t plus I sin omega t, and also e to the power minus I omega t can be written as cos omega t minus I sin omega t. So if I put it here, we can have A e to cos omega t plus I sin omega t plus B B cos omega t minus I sin omega t is equal to A plus B cos omega t plus A plus, sorry, that will be a minus I B sin omega t, and here A and B are the arbitrary constants. So A plus B or A minus IB also will be some arbitrary constants. So let us here define A plus B is equal to C, some arbitrary constants, and also A minus IB is equal to B. So I can write is equal to C cos omega t plus D sin omega t. Also here I can define T is equal to say some A cos delta and T is equal to A sin delta. So also from here I can define A is equal to over of C square plus D square, and delta is actually the tan inverse of D by A. So here I will put T is equal to A cos delta, and A is common in both E and D. So let's just take it as common. Cos delta cos omega t plus sin delta into sin omega t equal to is given as equal to A cos omega t delta. So what we have, this is one of the solution. This is the one of the standard form. A e to the power I omega t plus B e to the power minus I omega t. A and B are both the arbitrary constants. Here, this one is also also another form of the equation of motion, the solution of equation of motion. That is C cos omega t plus D sin omega t. And also it can be written here C and D are the arbitrary constants also. And here A and delta are the arbitrary constant. It also can be written as A cos omega t minus delta. So the same solution can have different representation. Okay, both are equivalent, and we can write any one of the form. Okay, so let's just summarize the general solution. What we have, that y is equal to a e to the power minus I omega t plus b e to the power plus I omega t, y equal to c sin omega t plus d cos omega t, and also it can be written as the form sin omega t plus delta or minus delta, or y equal to something like this. So all these three are the different forms. And here the capital A, capital B, capital C, capital D, small a, b, phi or delta are the arbitrary. This will be the delta one are the arbitrary constant, and we can define or we can find out the values of this arbitrary constant from the initial or the boundary conditions. Here, this A or B is actually known as the amplitude of the vibrate. This omega is the angular frequency of the vibration, and delta is called the initial phase. And for a particular problem, for a particular physical system, we can find out the vibration, we can find out the frequency of the system, we can find out the initial phase also. So one of the homework is for you to find out, you have to show that at t equal to 0, x equal to the initial conditions are x equal to x0. That means the initial displacement is x0 and the initial velocity is v0. And you need to find out if the equation, the solution of the equation of motion will have this. So please note it down and do it yourself. Now I am moving to how to find it, how to the acceleration and the velocity and the acceleration of the particle that is executing simple harmonic. So I already have derived that y is a can be written in this form. It can be sine, it can be cosine, it can be a summation, sum of sine and cosine. It can be, it has many different forms. You can take any one of them. From here, for this particular problem, I am using y equal to a sine omega t plus delta. Okay. So we know that the velocity is given by dy dt. So I am just differentiating with respect to t. Is it given by a omega cos omega t plus delta. And when the particle reaches to its mean position, that initial phase should be 0. So we have put that delta is equal to 0. So it will be given by v equal to a omega cos omega t. And we know that cos square theta plus sine square theta is equal to 1. Using this formula, we can write it down. It is root over 1 plus minus 1 minus sine square omega t. And if I simplify, we can have v is equal to plus minus a omega root over y1 minus y square by a square. So simply we have this form plus minus omega root over a square minus y square. At the mean position, initial displacement will be 0. And if it is executing simple harmonic motion, it will have at the extreme position, it will have the maximum amplitude. So we will find out the what will be the maximum value of the velocity, what will be the minimum value of the velocity at different position. So here this is the equilibrium position. At equilibrium position, what we have, the y, it should be 0. And at the extreme position, it will have the maximum amplitude, say y equal to a. And also this is one also is the extreme position, it will has minus a. Okay. So when the particle is at mean position, that is the equilibrium position, we get y equal to 0. So in this position, the particle velocity is maximum and it is given by v max is equal to plus minus a omega. And at the either of the extreme position, that is y equal to plus a or minus a, the velocity becomes 0. So at the middle position, it has the maximum velocity, and middle means the central position or the mean position or the equilibrium position. And when it is going to the extreme positions, the velocity becomes the minimum. And the opposite situation occurs when we will see when we calculate this acceleration. Again, to find out the acceleration, we have to differentiate the velocity with respect to time. So it will be given by minus a omega square sine omega t plus delta. And at, again we will put delta equal to 0 at the mean position. So in the mean position, the acceleration of the particle is given by f equal to minus a omega square sine omega t, or this a sine omega t is actually y. So I can write f is equal to minus omega square y. F is the acceleration. If you remember, for SHM, F is also always proportional to minus y. That is the rule of the SHM. And if y equal to 0, then the y equal to 0, that is at the mean position, the acceleration must be 0. And at the extreme position, the displacement is maximum. So the acceleration will be a omega square. Okay. So these are the value or the form of the velocity and the acceleration at different position. Okay. Now visualize the same thing using a graphical method. So here at that position we have the minimum displacement. Okay, fine. At the same time we have the maximum velocity and also we have the minimum acceleration, that is zero acceleration. And when it has the maximum displacement, it has the minimum velocity and the maximum. So this is also can be seen from the graphical, from this graphical representation. Now this is time for a concept test. So please pause your video and write down all these forms and try to find out which of the following functions represent the simple harmonic, which are the periodic but not simple harmonic, which are the non-periodic motion, and also try to find out the period of each of the periodic motion. Here omega is any positive quantity that you can find. Next, so we already have calculated, or we know the form of the velocity, we know the form of the acceleration. The next thing that we are gonna calculate, that is the energy of the particle executing simple harmonic movement. Okay. Now the total energy constitutes two parts. One is the kinetic energy and another is the potential energy. So first we will focus on the kinetic energy. So here the form of kinetic energy we know, Ek is equal to half mv square, and we already have derived this thing, the form of the velocity, that is given by this form. And if I just simplify this equation, we will get this one. So v equal to plus minus omega root over a square minus y square, or Ek is given by this thing, half m omega square a square minus y square. So this Ek is actually function of displacement. It is dependent on the value of y. At different values of y, the kinetic energy, the Ek, will be different. Okay. And similarly, we will calculate the energy, the potential energy part. Okay. Potential energy. So what we know, the force is given by F equal to kx, or also we know that it is m omega square x. And we know the differential work done is given by F into dx. So it is given by m omega square dx, where dx is the infinitesimal work done. Infinitesimal displacement from the equilibrium. So dw is the work done that is stored in the spring as a spring, and that will stored as the potential energy of the spring. So it is given by m omega square dx. Okay. So here Instead of x, we have used y. So let me just write it down. Ky here also is m omega square y. Say the infinite displacement is here dy, and so it will be m omega square dy. So this is the work done to display when it is displaced by dy amount of displacement. Now, so the total displacement is from the mean position, that is y equal to 0 to maximum. So it will be m omega square into y into dy. So the force is given by m omega square y into dy, and if you differentiate, we will get half m omega square y square. Let's erase this part. So EP, that is the potential energy, is given by half m omega square y square. Okay, so this is the potential energy that is stored within the spring when it is displaced from its equilibrium position, and the total energy at any instant of time will be given by Ek plus Ep. Ek is given by half m omega square a square minus y square plus this Ep already we have find out half m omega square y square. I already have told you that Ek is a function of displacement. It is dependent on the values of y. Similarly, you can see that the Ep is also a function of y. So if the position changes, the potential energy will also change. So if you just add these two terms, we will have half m a square omega square. Half is a constant. For a particular system, the mass is constant. So m is constant. A is the amplitude of the vibration, that is also constant, and omega is the angular frequency of the vibration. So this is also a constant term. So the total energy is a constant term. It does not depend on displacement or any other one. Okay, so we can say the total energy of the system is constant. And if I plot the potential energy and the kinetic energy, so from position to position it will vary. Okay, so this blue one is the plot for the kinetic energy. At the position, at the mean position, if you remember, at here at mean position, that y is equal to 0. So the the kinetic energy will have the maximum value. The kinetic energy will be maximum at the central position or the mean position or the equilibrium position. So from this graph you can see it has the maximum value at y equal to 0, that is the displacement, and it changes or reduces as it go away from the central position. So it is a hyperbole. And the opposite thing or opposite situation arises for the potential energy. It has the minimum value at the central position or the equilibrium position, and as it go away from the equilibrium position, the potential energy increases and it becomes maximum at the either of the extreme values. Okay, and whatever be the position, whatever be the value of this your displacement, the total energy is parallel to this displacement. So the total energy remains constant throughout the system as it evolves with the time. So since SHM energy oscillates between the kinetic and the potential forms, but the total energy remains constant. This is one of the important physical um, this is one of the important physical implications that we can understand from a simple harmonic motion. So SHM energy oscillates between the kinetic and the potential forms, but the total energy remains constant. Now, so the next topic is the LC oscillation. The LC oscillator, here we have the LC circuit that consists an L, that is the inductor, and one capacitor C, and they are connected in series, and here there is no resistance. And here we will discuss how there is a change, oscillatory exchange of energy between the electric field of the capacitor and the magnetic field of the inductor, and this will be called as the AC-LC oscillation of the free electrical oscillator. Before that, let me derive the differential equation of this electrical circuit. So here we will apply the Kirchhoff's voltage law. Here Vc is the voltage across the capacitor and VL is the voltage across the inductor, and since it is not connected to any energy source is equal to 0. And for capacitor, Vc is equal to Q by C, where Q is the charge accumulated across the capacitor and C is the capacitance. For the inductor, VL is equal to L di dt, and all of us know I is given I is equal to dq dt. So di dt can be written as d2q dt. Also Q, so here if I put the value of Vc, that is Q by C, and VL, that is L d2q dt square equal to 0, and if I simplify, this equation will be d2q dt2 plus 1 by LC into Q. And if you remember the general form of the simple harmonic oscillator, that was given by d2y dt2 plus omega naught square y is equal to 0. So this part 1 by LC is actually corresponds to omega square, where omega is the angular frequency of the vibration. So let me go to the next slide. The differential equation is of the form this d2q dt square plus omega naught square q, where omega naught is given by 1 by root over LC. So if I solve this equation, we can get q is equal to capital Q naught cos omega naught t plus phi. And also we can find out the time period and the corresponding frequency. And also from the Q we can find out the current, that is dq dt. So we can make an analogy with this electrical circuit with the mechanical circuit. The simple harmonic oscillator, that constitutes the mechanical vibration, and here we have a electrical circuit. So we can make analogy with this electrical circuit with the simple harmonic motion oscillator. So here Q, that is the charge, is equivalent can be compared with the displacement x or y. You can compare the current, that is dq dt, with the velocity v, that is dy dt. You can compare the inductance L with the mass m. 1 by C can be, that is the reciprocal of the capacitance, can be compared with the spring constant K. And already we have derived the form omega naught is equal to 1 by root over LC, that is equivalent for the mechanical vibration root over K by M. So some of the key points, these LC oscillations are free oscillations or the natural oscillations, and since no resistance is present, so no energy loss is there, so oscillation can continue indefinitely, and the frequency depends on the L and C. Okay, so let me understand the working principle of this electrical oscillator. So first, suppose this circuit, that is they are connected with the capacitance and the inductor, capacitor and the inductor. The capacitor is fully charged at a particular instant. Now the switch is closed. So what will happen? The capacitor will start charging the charge and a current will flow through the inductor. Okay, and inductor has a property that when the current changes within the inductor, it opposes the current by producing a magnetic field. Okay, so at the first time, at when the capacitor was fully charged, the total energy was stored within the capacitor and it was the electrostatic energy. Now the capacitor is discharging and current is flowing through the circuit, and as a result there is a opposing magnetic field through the inductor. So there is a change of energy between the L and the C. So electrostatic energy is converted into the electromagnetic energy, and the current is slowly building up. Okay, and when the current reaches maximum, when we have the complete discharge of the capacitor. Okay, and the whole electrostatic energy is converted into the electromagnetic energy. Okay, so already the capacitor is fully discharged. Now at this condition, the magnetic field begins to collapse within the inductor. So the back EMF of the inductor keeps the current flowing through the capacitor in the same direction. But the capacitor starts charging, but with the opposite polarity. So as the charge is building up through the capacitor, so the electrostatic energy again building up, and the magnetic energy is decreasing because the current is decreasing and the corresponding magnetic field also decreasing. So there is a transition between from the energy of capacitor to the energy of inductor, and also vice versa. Okay, so there is a oscillations, and this process repeats and produces oscillations. Okay, so at the time, at any time, the total energy in the circuit will be constant, and electric energy oscillation oscillates between the electric field of the capacitor and the magnetic field of the inductor, while the total energy remains the constant. So here the blue one is the electric and the energy of the capacitor, and UV is the energy across the inductor. And if you sum or if you add both this red one and the blue one, you will get the green one, and that is a constant. And this is similar to our total energy of a simple harmonic oscillator, where there is a oscillation between the kinetic energy and the potential energy, while the total energy remains constant. Same thing is happening in this LC oscillator also. So there is a energy exchange between the capacitor and the inductor, and energy oscillates between the electric field of the capacitor and the magnetic field of the inductor, while the total energy of the system remains constant. So let me summarize this lecture. So what we have learned, that is the basics of the simple harmonic oscillator, and as we have not introduced any damping term, so the SHM will oscillate indefinitely with the constant amplitude. And but this is an ideal case, okay, that we do not see in our real life problem. What we see, that in reality, actually after a certain period of time, the amplitude of the oscillations always decreases with the time and the oscillations die out. So in this next lecture, we will continue our discussion. Thank you for listening.